The floor is to you. Thank you very much for the kind words of introduction. Thanks to Vector for awarding me the opportunity of speaking to this topic that has been with me for some time and give you a short presentation about the industrialization of test benches. To start off with, I should like to talk about the agenda first. I would like to introduce Magna Powertrain Systems. This is a division inside the Magna Group. After this, I should like to introduce our project proper that I want to talk about in the next minutes to come, in particular with respect to the realization of test benches on the basis of vector function call framework. And then I'll briefly talk about what we did. I broke it down with respect to Canoe Gateway and the interface for this, the Canoe client. And finally, I should like to talk about the benefits, also from the point of view of production, what came out of this project for us. And furthermore, how from a small project that started a few years ago here in Stuttgart, which we've rolled out globally meanwhile, and that makes currently up a major part in the operation of our test benches. And last but not least, I want to talk about plant extensions, because development never stops. So any extension items, what's the future hold, in particular things such as Industry 4.0, big data, etc. Briefly on Magna. Meanwhile, we are one of the biggest automotive suppliers worldwide. We've been around for 60 years roughly, and currently our global presence amounts to 172,000 employees in more than 340 different assembly and manufacturing sites, plus more than 93 different engineering or development centers, which are dealing with this aspect in more than 28 countries on 4 continents. Brief overview where I come from. I come from the Magna Powertrain driveline systems. We are working in the powertrain field. Our core competency is in the manufacture of different gearboxes, rear axle drives, transfer cases, and also electric axis is one thing that comes up more and more. Transfer cases as well. Where are we based? I come from Graz now. We have Ilz, Lannach and Albersdorf sites nearby in Austria also, and I'm in charge also in sites for sites in Germany, Retsch, Lenzing in the United States, Ramos in Mexico, and last but not least, China with Shanghai. Okay. Question: has anyone seen a powertrain assembly process? Can you imagine what that looks like in industrialization, industry, or in a factory? I'll try and show you. This is a typical assembly of a transfer case. As we have it in dozens of our factories. This is based on the latest lean requirements. Production starts here in this sequence. The casings are put together, measurements are being carried out, then setting discs are measured, and last but not least, my area comes up once the transfer case is married with the controller, with the ECU. There's a flash station. What does such a flash station do? It's in charge of well, it's an ECU that's used for different customers, and it has to make sure that the proper application is used, and then everything is marked. And after this, we have our test bench here. Typically, this consists on a body sound measurement, NVH, and clutch test bench where we are measuring different measuring points on the clutch, structure bone noise, etc. Such a flash station, this is what it looks like. We've got different variants here. Here at the bottom, it looks rather standard, which is a station with 4 nests, and in the background is with this station we are flashing 500,000 ECUs per year for 7 to 8 different OEMs and with different software on them each time. On the other side here, you can see that we have a so-called inline flashing station, which is online, or which is inline in our assembly systems. 200,000 units per year are being flashed, but mostly it's one customer with one dedicated ECU and a dedicated software. The principle of it all is normally we are getting our ECUs from sub-suppliers. Normally it's just the hardware with a point loader. With a bootloader, so we have to put the code on the bootloader, apply the software, and we have to make sure that different logistics data and other ecom values are written properly and were saved properly. And in addition, we have a marking on the ECU. It could be a label with different part numbers, or also the software status. Next, this is our typical test benches, shown more in detail. On the left-hand side, you can see our so-called NVH test bench. Also, NVH stands for noise, vibration, and hardness. The primary purpose for these benches is measure structure-borne sound, the tensioning of the gearbox, and that's the structure. And we have to make sure that we are measuring the structure-borne noise from the gearbox and not from the test bench. We have on the right-hand side our clutch test bench, which we use for transfer cases, with a lamellar clutch, with having several measurement points here. The ECU is classed accordingly so that we can check that we meet our requirements for accuracy of set points for the front axle. What's important is that these tests are done for every gearbox and transfer case. We are measuring 100% for NVH and for 100% clutch accuracy, and accordingly this is quite an effort and cost. If you just imagine that 200,000 transfer cases are produced on a typical assembly line, we are talking about cycle times of 60 to 70 seconds, in which one of these transfer cases must be tested 100%. This is why it's so important for us that our processes are optimized all the time, and that we clearly define what is to be tested, what are the requirements from the customer, how do we ensure that assembly is done properly, and that we can detect potential defects. Okay, as an example from our electrification line, I've got a typical system test here, system test bench. This is used for electrical rear axles, as we have been that have been coming up more strongly recently. This is one of our most complex test benches that we are using, because we don't have we don't have a gauge test here, but we have tests for the motor, BEMF, back electrical magnetic force, 3-phase short circuit tests, where voltages and currents are recorded, constants are worked out, which have to be within certain tolerance bands. And last but not least, a certain active power test is performed. We go to certain load points, certain speeds, RPMs, etc. And so we make sure that we can ensure the active power that corresponds to the customer requirements. Something that's new, that's ISO 26262. When I started, that was just a topic which was important for and relevant for development, but it's come into production now as well, and we have to make sure now that we have safe status of the gearbox or the powertrain at certain conditions, and we have to test this 100%. What were our challenges in the past? We have different types of customer. We as a supplier, there are German OEMs, there are British OEMs. What was the state of affairs so far? Each of them had their own hardware, their own software, tool chain on it, and most of it was designed for development purposes. Nobody actually ever looked at, is it possible to standardize it? Is there an application programming interface for it? MA was never a topic. This was purely for development. Nobody ever thought about how stable the whole thing is, how fast running is it, and what do you do when there are defects or bugs or errors, how can we respond quickly, and how can we start taking action immediately. Big problem that there were some years ago was the knowledge. The worst case that I can remember, we as a supplier were supposed to supply to a big OEM in Munich, do the test bench for the transfer case. Unfortunately, there with the OEM, there wasn't the know-how. They had a sub-supplier that did their test benches for them. Until at the time we received a specification, what we needed to implement and how it was meant to work, just for a transfer case test bench, where the simple functionality was, I want to commission it, I want to calibrate it, switch on and off a few measuring points, but it took months. And in the end effect, what did we get? A 500-page test bench specification, what step had to be implemented in detail, how the residual bus, etc., had to be handled, and all of this then we passed on to our suppliers, who were mechanical engineers. They know everything about steel engineering, construction, control engineering. But when it comes to automotive, CAN, FlexRay, CAN-FD, never heard of it. At the time, that was the business where I said, okay, we can't go on like this. We have too many interfaces. The system is much too complex. We don't have an opportunity of do this with acceptable cost and effort. So the question was, what can we do that we have fewer interfaces, clearer separations in the future, and the same functionality and the same functions that different customers want to have in the same way, we can have them in the same system. And after this, a number of years ago, in 2014, in coordination with Vector in Stuttgart, the idea to the Vector function called framework was created based on the VN89XX platform. Briefly, in terms of introduction, at the time, in 2014, we started with our requirements. The objective that we had was that we wanted to have a simple interface, never mind for what client, whether the client is a mechanical engineer in Germany, Austria, or United States. All they want us to do is to commission their system, calibrate it, etc. So make a simple interface available to them that they can actually use in any other project to come. In addition, we also know that for each client, we still have to build something customized to make sure that the residual bus simulation is available, certain functions and features are available, fault diagnosis, flash situations in order to be applied for the ECUs. And in addition, to have flexibility so that when there are changes, we can modify it without a lot of effort and can use them again for other projects. And our objective was that we break it down into so-called Canoe Gateway, which is then in charge just for residual bus simulation, doing the measurement, flashing functions, support EOL functions, which are part of the Canoe gateway. Then, by way of Ethernet, UDP, so the FDX protocol, communication must be possible with this device, always have the same interfaces, de facto, and it's easy to handle. Additional requirement that we had to our test benches is there is a lot of different hardware that we need, and a lot of different information needs to be read in, just like RPM speeds of the motors, or the engines, or the torque measurement sensors, so we have to have the certain torque measurement points, etc. Important point that we had with this system was that it had to be standardized, and we move away from all of these island solutions. And this is why, when it comes to the hardware, we arrived at 2 solutions now that we stayed with. We said, okay, we'll only use the VN91X platform. There were 2 solutions for our applications, our use cases. On the one hand, the VN8910, or now its successor, the 11, which we normally use for test benches only. And here our objective was to have a small and straightforward solution that we can use for various purposes. On the other hand, not every project could be covered by this. There are customers with higher requirements. One of my favorite customers from Munich again, who made me start sweating every now and then. In particular, the flashing was an issue at the time. How long did it take with the customer bus? Sometimes some minutes and more. If you just imagine, I need 2, 3 or 5 minutes to apply my ECU software completely. When it comes to 1 million pieces, you can imagine how many stations you need for you to be able to cover this in series. In addition, there were always so-called high-end applications where corresponding the residual bus communication or diagnostic communication required certain standardization. Recently, e-mobility products came up, and they have higher testing requirements. So, what does it all look like now on the Canoe gateway? So, we called it our Canoe gateway. All of this is running on a VN89XX. What's important here, we're using the standalone mode. That's to say, we in production get special developments only in the runtime environment or configuration for it, and correspondingly flash packages, completely finished. We have 1 or 2 of them. We have to play them in, and the whole system is up and running. When it comes to development, we are using Canoe version 11 for preparation. The most important thing that was positive here was the residual bus simulation topic. Canoe supported this wonderfully. It used to be 3 to 4 weeks for the implementation of residual bus. Now there is the interaction generator function. Mr. Brentler, I was quite surprised. After 3 days, we had a complete residual bus configuration, and it all worked on our test bench wonderfully. I was very enthusiastic about it. What else do we have on board? Diagnostics communication. Every manufacturer, I mean, there are the standards. Who actually uses all the standards? Is it UDS? We still have some KWP 2000 projects or other formats with the ODX and CDD process. Most important item here again, we do so-called functions. That is to say, the functions always used to be synchronous functions, and in order to run certain routines, so that we got a corresponding feedback. Another thing that we needed was the so-called signal measurement data recording. So we use the signals from ECUs or from peripherals, motors, measurement sensors, etc. And we have the possibility now for up to 200 signals with 200 hertz of the strongest configuration to be logged in one go. On the other hand, we got our so-called GNU client. This is what we call the net assembly. So we had configured very lean interface assembly that we can actually use for the entire system. We made the distinction here. I've got a transfer case, I've got a rear axle, I've got a double speed gearbox where I need certain functions. We were able to do this with a complete control system for the test bench. We have 15 different methods, which would be acceptable to most of our OEMs. Also the flashing. We used to have X number of protocols together with the Y-flash. It was very easy to implement it. We just need 5 methods now: bootloader applications, flash package, etc., to be booted and executed. What's our current setup of the test bench look like now? We have a host computer normally, on which we have the host system, and that we got from the test bench manufacturers, and they integrated our GNU client as the library. As a standard, VN8910, or now the 11, is being used as hardware. GNU is running in standalone extended mode. Depending on the project, we have 1 to 2 FlexRay piggies, and for the peripherals, we have 2 to 4 CAN piggies. What's also very important, I/O piggies to be used. Well, we've got 1. What do we need it for? In order to make sure that the ECU is woken up correctly and sent to sleep correctly. And in this case, we have included a current and voltage measurement, which we use for complete wake-up and sleep mode. We have certain relays that can be switched, and certain measurement signals can be read in. What about our flashing? Same solution again. There is a central host computer which uses the GNU client again. Here we have mainly VN8912 or VN8940 as a hardware, GNU in the standalone mode, in addition now vFlash Station, and in addition to the traditional variety, clearly more ECUs can be flashed in parallel. What were the big benefits that we were able to gain in production due to this? Now finally, we have the same tool chain for different customers, hardware and software. Most important thing, it's in engineering and production environments. It's identical, and we have the know-how is now internal. Another bullet point here is the implementation effort from test bench supplier has been reduced. They get a ready-made product. They only need to embed it with the corresponding interfaces. We've saved a lot of cost, and we also saved a lot of time with respect to certain customer milestones. Another important thing is that with this system, because it was the first time that we were fast and flexible when it comes to changes on software during the assembly process. You had to replace or interchange 2 files, one for the flashing process, and one for the GNU gateway. We were able to reduce the flash times from 2 minutes. We came down to 35 seconds now, which for us in mass production is a major benefit. Meanwhile, due to this, so-called Magna standards have been developed. There's one for flashing and one for vector communication. What we are particularly proud of is that meanwhile we have rolled this out worldwide in the complete Powertrain driveline systems division with a small number of core team members. We have now been able to extend it to 23 projects for 13 different customers worldwide. Here in Europe alone, we have 7 projects distributed to 4 sites. 90% of our current projects are covered by this. In North America, it's a little less still. We only have 5 projects there on 3 different sites, on about 70% there. And what's very much up and coming now here, also in Asia, we founded a new joint venture for this for the topic of electromobility. What do we want to do in future? Now we've industrialized all of this now. You end up with enormous amount of data. Almost 2 million gearboxes are leaving the plants with a lot of data for them. So what can we do with all this data that we've recorded, that we've saved, so that we can use them for our conclusions? At the moment, we are in the process of organizing a big data project together with Vector VMDM, Vector Measurement Dimension System. And we started a Microsoft Azure integration, and we started a machine learning project. Further items that are getting more and more important is third-party tool integration. What's been demanded from our development is that we do signal analysis. Here we want to integrate Python, and the idea is that also for the GNU open environment, we may be able to use this for the corresponding kinds of projects. Example of what data we want to analyze: NVH data analysis. This is the FFT, fast Fourier transformation analysis for certain data. For clutch characteristics, there are certain characteristic curves. What's the distribution? What is it currently? Has it shifted? If it has shifted, what were the reasons for the fact that it has shifted? Data for the data, raw data analysis, most different kinds of data. You can see them here. We have up to 50 megabytes of data, which are recorded for just one gearbox. And you can imagine that it's quite an effort to actually analyze it and come to conclusions. Okay, that was my presentation on this topic. I hope I didn't overshoot my time too much. No, not too much. Any questions? Thank you very much for this clear view of mass production and the 100% testing processes. Are there any questions from the audience? Third and fifth and sixth row.
Thank you. Actually, I have 2 questions regarding timing. First, you mentioned that this solution helped you to reduce the flashing time. Maybe if you can elaborate more, how did this affect the flashing time?
Firstly, we have, for example, only used customer tools that were especially designed for engineering. There were a lot of different steps that were executed that we did not need in production, or it was, for example, a sequential procedure. We are flashing first the bootloader, then the application, maybe later on we make the parameterization. And then we have decided, for example, to switch to so-called image flashing method, which is much faster.
That's great. And the other analyses, you mentioned the clutch analysis and the 50 megabyte data analysis.
Yeah.
Are you doing this as part of the end-of-line testing?
Yes, we are doing this as part.
So did this affect also the execution time of the end-of-line testing?
At the moment, this data is stored on a database, and the analysis is done later on. So at the moment, it's often a manual analysis. We export certain data once a month, once a week, depending, and then we create some analysis based on MATLAB models or DODM, for example.
Thank you.
Dritte Reihe noch. Mich würde noch interessieren.
I would be interested in learning this big data analysis. Is this in order to improve the product, or also to improve the production process? Well, both. We have very often the problem that the customer complains that with a certain gearbox a certain problem occurred, and then we normally get the gearbox sent back. We do an initial measurement on the test bench and we do a second measurement. And all this data that we create gives us the opportunity to make conclusions that there might have been certain pulsation in the curve, there was some fluctuation, the amplitude was too high, etc. What do we want to do? The question comes time and again, are there other gearboxes that have the same behavior? And for this, in retrospect, we would be able to analyze this data a lot faster and more efficient. Up to now, it's manual and it's very cumbersome and takes a long time. Any more questions? So I should allow myself to ask a question. The planning times could be significantly reduced. Can you tell us how much? Well, that varied. On average, we had a saving here of 3 months on the test bench. Why? Because all of this was produced for our test bench purposes in the development phase, and we were given a ready-made testing environment for the test benches during production, during development, so we could actually test them a lot earlier. So we had pre-acceptance. There's new software. Please take a look at it and make sure that it works, and it did. Any more questions? If this is not the case, I should like to say thank you very much to you, Mr. Haring.